Good day. My name is George Bowden, and today I will be discussing my simulations of the ionospheric response to atmospheric waves generated by rockets. As rockets pass through the upper atmosphere, they can affect the ionosphere through several mechanisms. These include changes in chemistry and atmospheric waves in the neutral component. Acoustic and gravity waves are generated as the rocket exhaust plume expands, interacting with the surrounding thermosphere. The thermospheric waves then result in travelling ionospheric disturbances. These ionospheric perturbations are simulated here using an Ionosphere Thermosphere General Circulation Model. The aim of this work is to assist in the prediction, detection and interpretation of these rocket-produced ionospheric disturbances, and furthermore, in order to provide a test of atmospheric models and a means to probe the conditions in the upper atmosphere. Waves in the thermosphere can affect the ionosphere in several ways. Both acoustic and gravity waves result in perturbations to neutral winds. The motion of neutrals results in ions being dragged up and down magnetic field lines due to ion-neutral collisions. This leads to compression and rarefaction of the ions. Moreover, for longer period waves, the change in altitude of neutrals can result in changes in the loss and production of ions. Both of these effects can be considered using a general circulation model. Another effect known to be significant is the change in the dynamo effect, which is communicated up magnetic field lines from lower regions of the atmosphere. This is not considered in the simulations which have followed. Over the past half-century, propagating ionospheric disturbances have been observed on many occasions. Measurements have been made using GNSS time delay, ionosondes, and Faraday rotation of geostationary satellite signals. These disturbances can be detected regardless of local time, season, and geomagnetic conditions. Circular and V-shaped disturbances are possible. Indeed, both are seen in the example on the right of this slide. The disturbances can propagate with various velocities and periods. This leads to association with multiple different kinds of waves, including shock acoustic, guided acoustic, and acoustic gravity waves. In this presentation, I will outline simulations of the Jason-3 and FORMOSAT-5 satellite launches. Both occurred on Falcon 9 rockets from Vandenberg Air Force Base into polar orbits. Simulations were performed using the Global Ionosphere Thermosphere Model, a general circulation model of the upper atmosphere. Unlike most comparable models, GITM uses an altitude-based grid and does not assume hydrostatic equilibrium. It is therefore capable of realistically modelling acoustic waves. Mass and thermal energy sources were added to GITM. Multiple runs were performed, 4 sources at various different nodes representing points along the rocket's trajectory. GITM was initialized in each case using the IRI and EMSIS empirical models. TEC perturbations from each of the simulations were superposed and then filtered using a zero-phase bandpass filter. The derivation of the temporal profile for the sources is outlined on this slide. The analytical expansion model of Bowden and et al. Was used to determine the exhaust plume characteristics. These were then used to determine a pressure temporal profile in accordance with the weakly nonlinear theory of GITM. source amplitudes could then be derived by equating the monopole and analytic plume acoustic energy fluxes. In this treatment, the nonlinear steepening of the waves, or aging effects, were ignored. Atmospheric parameters for the Jason-3 launch are displayed on this slide. These include the timescale of the plume, essentially the time required for the plume to pass a particular point in space, TA, the maximum period of acoustic waves, TB, the minimum period of gravity waves, L, the length scale of the plume, lambda A, the maximum wavelength of acoustic waves, and H, the scale height. Results of the GITM simulation are shown on this slide. On the right-hand side, we have an animation showing the changes in total electron content over time across the simulation domain. On the left-hand side, we see changes in total electron content along particular lines. The upper plot shows changes in TEC along a meridian, whilst the lower plot shows the changes in TEC along a line perpendicular to the rocket's ground track. These results show a transition from initial fast V-shaped perturbations to slower circular perturbations towards the end of the simulation time. The GITM simulation can be compared with GNSS measurements due to LIN, as well as the ray tracing simulations that I have performed previously. In the meridional plot at the top of this slide, LIN identifies multiple concentric travelling ionospheric disturbances. These are each associated with gravity waves based on the dispersion relation and atmospheric conditions evaluated from MSIS. Ionospheric disturbances with decreasing phase velocities are also apparent in the GITM simulation. However, there is some difference in that there is a clearly identifiable acoustic wave in this simulation, and the latter, presumably gravity waves, have a higher phase velocity than the ones in the measurements of LIN. The lower plots show TEC variations along a black line perpendicular to the rocket trajectory. LIN identified the ionospheric disturbances in this plot as being due to acoustic waves. The period of the disturbances seen in the GITM simulation fairly closely matches those seen in the GNSS measurements. However, the GITM simulation produces much slower phase velocities than do the GNSS measurements. It's noted that the ray tracing simulations that I previously performed agreed much more closely with the results of LIN. Such a discrepancy may indicate a significant difference in the temperature or electron concentration profiles from those of the empirical models. We now move on to the simulation of the FORMOSAT-5 launch. The atmospheric parameters for this launch are shown on this slide. This launch was somewhat atypical in that it launched directly to mission altitude. This resulted in a very steep trajectory through the thermosphere and ionosphere. This results in very large circular ionospheric disturbances which propagate away from the rocket's trajectory. These are evident both in the GITM simulation as well as in the GNSS observations of Cho et al. The results of the GITM simulation can be compared quantitatively with GNSS measurements and with ray tracing simulations that I have performed previously. Cho has identified the ionospheric disturbances seen following the FORMOSAT-5 launch as being due to acoustic waves. Both the GITM simulation and GNSS measurements give similar values for both the period of the waves as well as their phase velocity. This contrasts significantly with the ray tracing simulation, which greatly overestimates the phase velocity. In summary, I have implemented mass and thermal energy sources into GITM and used these to simulate the ionospheric perturbations due to rocket launches. These simulations have reproduced periods and qualitative features of rocket launches observed in GNSS observations. The GITM simulations produced phase velocities which were closer to GNSS observations than were the previous ray tracing simulations I have performed. However, the GITM simulations significantly underestimated the phase velocities of acoustic waves for the Jason-3 launch, suggesting that perhaps EMSIS underestimated the thermosphere temperature in that case. In future, I would like to use a more realistic acoustic source based perhaps on computational fluid dynamics or a direct simulation Monte Carlo approach. Furthermore, it would be good to specify the lower boundary of the simulation using ray tracing as opposed to implementing a monopole source. This would more easily allow the estimation of the appropriate amplitude of the source. Furthermore, I would like to replace the total electron content perturbation calculation with that from GITM with a more advanced model that includes ionospheric electrodynamics, including the dynamo effect, such as SAMI2. In future, I would like to apply the methods developed here in order to fit thermosphere temperature profiles. Thank you very much for your time.